Yeah, so hi everyone. Let's wait for 2-3 minutes more to join others, and then we will start. Yeah, good evening all. So today is the open session for week 4. So if you have any doubt in any particular topic, so you can ask. You can just raise your hand and you can ask. I'll note down your topic. Then we will discuss the topic. So is there any specific query about any specific topic? Hello, am I audible? Hello, can anyone confirm? Am I audible?
Yeah, yes.
Okay, okay. So any question related to week 4, if you have, then you can ask any particular topics, or we should revise all the things of the week 4.
Better to revise some of the topics.
Okay, okay, okay. So we will.
Sir, just a conceptual briefing.
Sorry, Sasi. So can you repeat?
So just a conceptual briefing of the topics.
Concept of the week 4 topics.
Just we'll go through the concepts.
Okay, okay. Okay, so we will start from the basics of the week 4. So I have a summary page. So we'll take the help. So yeah, so week 4 is basically introduce the graph. So what is the graph is? Graph is basically a non-linear data structure, and it consists of a non-empty set of V. What is the V is? V is a set of vertex, and V also contains the collection of edges in this group. So here we are mentioning the E, capital E. We are representing the capital E is a collection of edges. So we can represent a graph using G equal to V comma H. So V is here the set of vertices and set of edges. So you can see the one example of the graph here. So here is one graph. So there are some vertex. So here A, B, C, D are vertex. We are representing in the circle. And there are some edges that are connecting to these vertex. We are representing these as by some name E1, E2, E3, E4, E5. So we can represent this graph in some different forms. So there is one form. This is called the set forms. So here G equal to capital in round bracket V comma E. This is the total representation of the graph, where V equal to set of vertices. So we can represent these vertices in the set forms. A, B, C, D, E. These are the sets. And same things. E is the collection of edges. So we can represent the edge via the edge name. So here we have mentioned the name for every edge. So we are representing the each edge in the set, and also we can represent the edge using a round brackets. So here A comma B. So A comma B in the round bracket is representing that there is one edge which are connecting between A and B. Okay. So we can written either in A comma B and B comma A for this graph. So both are representing the same edge. So we will not include the BA in this set because both are representing the same edge. So we can represent our edge in this form, round bracket A comma B, like this. So after that, so there are some different types of graph. These are some common categories of the graph which we will use in our week 4 and week 5. So both are related to the graph concepts. So first thing is first graph is representing the undirected and unweighted graph. So if our graph simply representing the vertex and connected edge, and there is no direction given on the edge, and there is no weight assigned on the edge, so that is called the undirected and unweighted graph. Second category is directed and unweighted graph. So that represent that if we have a direction on the edge, okay, so we can call that this is a directed graph, but there is no weightage assigned on edge. So because of that, we are mentioning that directed and unweighted graph. So third category is undirected and weighted graph. So here, here only weightage are given on the edge, but direction are not given. So because of that, we are calling that undirected and weighted graph. And fourth category is directed and weighted graph. So here direction and weight both are given on the edge. So because of that, we are called that directed and weighted graph. So these are some categories of the graph we will use in our upcoming concepts. Now the second thing is this is the theoretical representation, but how we can represent the graph in our programming. Okay, so for make a program for the graph based problem, so how we can represent the graph. So there is graph representation unweighted. So how we can graph represent unweighted? Yeah, so there is no weightage given on the edge. So for directed graph, so this is a directed graph but unweighted graph. Okay, so how we can represent? Yeah, so this is also a set representation. Yeah, so previous representation is given for the undirected graph, but this representation is given for the directed graph. Yeah. So yeah, so we can represent G equal to V comma E, V equal to set of vertices. So here there are 5 vertices is given, 0 to 4, and then there is a set of edge is given. So 0, 1, 0, 2. So here now this is a directed graph. So here we can represent so we will represent these as via 0, 1. So here 0, 1 representing that edge is starting from the 0 and ending on the vertex 1. So we cannot represent this edge via 1, 0 because here direction is given. So here where the edge coming from and where the edge reaching to. So these things are we should carefully mention in our edge set. So 0, 1 is representing that there is one edge is coming from 0 and reaching to 1 vertex. Same for 0, 2, there is one edge 0 to 2. So we cannot represent this as 2, 0. That is the different direction edge. So here direction, so in undirected graph, we can represent either 0, 1 and 1, 0. So because direction is not given, so both are representing the same edge. But here 0, 1 and 1, 0, both are representing the different edge in the directed graph. So these are the theoretical representation. Now after that, how we can represent these graph in our programming language. So here some vertex is given B. This is the list of the vertex. There is one E. This is the list of tuples, and each tuples is representing an edge. So we can represent our graph in two forms. One is adjacency matrix, and second adjacency list. So what is adjacency matrix? So we use the two-dimensional matrix for representing the graph. So here we can create a two-dimensional matrix using a NumPy, as well as we can create a simply two-dimensional list. So here we are importing a NumPy as NP, and there is one, we are creating a zeros matrix of size, comma size. Here size of the so there are 5 vertices, so we will create a matrix of size 5 by 5. After that, for each edge, if there is an edge between any two vertex, we will assign the value 1. If there is no edge in between any two vertex, so we will assign the value 0. So that is the representation of our graph in the adjacency matrix form using NumPy. So here the row represent the vertex and column also represent the vertex. So we can find out the any edge by combination of row and columns. So any cell, for example, this. So this is the one vertex. So this is the first row. This is first node. So this is one row. If we are starting the row from 0, so this is the first row, and this is the second column. So is there any edge between the one vertex and two vertex? So this 0 value is representing this information. So if that value 0 is representing that there is no edge between one vertex and two vertex. So if, for example, this one, so this is representing that there is one edge between one vertex to three vertex. This is the third column. So one vertex to three vertex, there is an edge. So this matrix is basically for the undirected graph. So this is for directed graph. Okay. So this is for the directed graph. That means so there is one edge from one vertex to three vertex. Okay. So if the graph is, for example, if this graph is a undirected graph, so at the time, so there is one third row and first column is also containing value 1. So we can represent our graph using this adjacency matrix. We can create this adjacency matrix using NumPy. So same thing, we can also create this matrix using a list, nested list. So here we are creating a loop. So I in range of size of the vertex, and we are creating here row, and we are just assigning a 0 value for each column in the row, and then we are appending these row into our main matrix A matrix. So we are creating a nested list here to represent the our graph in adjacency matrix form. So we can use any one of them in our graph. So same, this is output. So yes, this is the same. Now second representation is adjacency list. So we can create a adjacency list using a dictionary in Python. So here this is the same information. This is list of vertex, and this is a list of edges. So here each tuple is representing the edge. So same things, we will create a dictionary here, and each key is representing a vertex, and each value corresponding to that key is representing the edge from this keyword text. So here, so for example, if we are seeing the output here, so this is representing the information 0. This is 0 is key, and there is a one list 1,2 is a value for that 0. So here this representing that there are two edges from 0 to 1 and 0 to 2. So we can represent this information as information in a dictionary, and we can use this adjacency list in our program. So these are two type of representing we will use in our all the concepts we will learn in the week 4 and week 5. So adjacency list and adjacency matrix. So same for the undirected graph. So we can represent the all these things using NumPy array, nested list, and same for the adjacency list using a dictionary. So we can represent in these two formats. We can represent any graph in these two formats in our program language. Now after that, the first algorithm is discussed in the lecture in the week 4 is graph traversing algorithm. So for example, if we have a graph, so how we can traverse all the nodes? Okay, this is just a traversing. Traversing means we want to access all the nodes of the graph. So how we can perform this operation? So there are two approaches to traverse algorithms are breadth first search, in short we call BFS algorithm, and second is DFS, depth first search algorithm. So the name representing the approach also here. So breadth first search. So how we can represent this breadth first search? So for example, if we have a graph, so I'm creating a graph. So what is BFS? Actually, first we will learn the concept of BFS, then we will see the implementation. So there are some vertex, yes, 0, 1, 2.
ক্লাস চলছে একটুখানি যারা 5 মিনিট যদি চলে আসে একটুখানি আমি দেখলাম 10 মিনিট দেখালো লাস্ট
Also, please turn off your mic if you are not asking any questions. So, Akash, Parmita, Anurag, all mic is open. Okay. Okay. So we are just creating a graph. So here there is one S1. Okay. So yeah. Check, please. So we have a graph now, and we want to perform BFS algorithm on that graph. So what is the concept of BFS is we can start traversing from any vertex. Okay, so for example, we can start from 0. We want to start from 0, and after starting point, if we have selected the starting point, then we will traverse the node by adjacent. So label by label, we can say that we will traverse the node label by label. Here, what the label is representing? So label is representing the adjacent node. So for example, if we are traversing 0 first, okay, then after that we will traverse all the adjacent of the 0. Then we will move further. Okay, so we will, if we are starting from 0, so after that we will traverse 1 and 2. So after completing this all adjacent of 0, then we can move further. So first is 0, then we can select any of these two adjacent in the second case in the traversing. So we can traverse first and then traverse 2. We can also perform like this 2, 1. Okay, so there is no foundation to traverse the order of the adjacent. So there is one condition is that we will complete the traverse or on the adjacent level. We will complete the traverse of adjacent nodes first, then we will move further. Okay, so first after traversing 0, we can traverse either in this way and then 2 1 0 2 1 0 1 2 and then 0 2 1. So now 0 have completed, all adjacent of 0 is also traverse. Okay, now we can select any of these adjacent and then we can check that the next adjacent level. So now if we create a tree, so the tree is not introduced, I'm just using the, we can say that the hierarchical form we can, if we can create. So we are starting from 0 and then first level is 2 and 3. So after completing this, so this is level 0, this is level 1, we can say. Okay, so After completing the adjacent nodes, then we will start the next adjacent label. So next adjacent label is the adjacent of the child nodes of 0. So if we have traversed 2 and 3, sorry, 2, not 2, 3, 1 and 2. Okay, 1 and 2. So we will check that what are the adjacent of 1. Now what are the adjacent of 1 is, so 0 have already traversed. Okay, so we will not repeat this node again. Those nodes are not visited. We will check those nodes only. So what the adjacent of 1 is 3 and 4. Okay, so we can select either 3 first and then 4. Same things, we can select the 4 first and then 3. So we will complete the traverse. So if we have reached the 1, then we can traverse 3, then 4, like that. This is the label, next label. Now we will check the second. So we have completed this one, we have completed this one. Now we will check that the second adjacent node of the 0. Now and check that is there any node available which are not visited now. So the adjacent node are of the 2 are 0, 3, 4. 0 have already visited, and 3 and 4 are also visited by the node 1. So there is no node available which are not visited. Okay, so we will skip this part. Then we will check the next level nodes 3. So this part is complete, this part is completed. Now we will check the third, this 3 node. Is there any node adjacent node available which are not visited? So how many adjacent are available? Of 3. So 2, 1 and 4 all are adjacent, are connected, but 2 have already visited, 1 have already visited, and 4 have also already visited. So all nodes are visited. Then we will skip. Then we will check the next node 4. So the adjacent is 3, 2, 1, but all are visited. So this part is also complete. So we are visiting nodes label by label. So we are starting from 0. Then we are visiting the adjacent node of the 0. All adjacent completed. Like in that way, we can traverse like this. In that way. So this is the first level. This is the second adjacent level, and this is the third adjacent level. Okay. So we are traversing the node adjacent level wise. So this is the approach of BFS. And how we can implement this approach in our code programming. So we can use the queue data structure for that. Okay, so yeah, so we can use the queue data structure. So these are important questions. So what data structure is suitable for the BFS? What data structure is suitable for the DFS? So this is the most common and asking question in the interview and the completion exam type. So we can say that the queue is the most
hold on, नहीं खोल पा रहे हैं.
Yeah. So we can say that the queue is the most suitable data structure to perform this BFS algorithm, and also stack is the most suitable data structure to perform DFS data structure. So DFS algorithms. So we will take the queue. Now we are just revise the concept how we can perform using this queue initially. So this is the first part. We are starting from 0. We will take one queue. This is empty initially, and all visited value are false. This is the initial condition. All these are representing, index are representing the nodes here. 0, 1, 2, 3, 4. This is representing the nodes, or we consider a vertex. So initially all are false because no node are visited, and queue is empty. Okay, we will take the queue, and that is empty. If we are starting from 0, we will mention that we will insert this 0 vertex in the queue and mark that this 0 is visited in our visited list. Okay, we can use the dictionary also. We can use anything, any data structure to contain this information, visited information. So here we have mentioned that 0 is visited. Now we mark that true. Now that we will check what is the next adjacent level. So we can check that there are two adjacent nodes, 1 and 2. Okay. So adjacent node, we will mark that 1 is the adjacent and 2 is the adjacent. We will insert these two adjacent in our queue. First, we will remove there's one slide. Okay, missed. Yeah. So it started 0. So we will remove the 0 vertex from the queue first. We will mark that 0 is visited, and we will check that how many vertex are the adjacent of this 0. We will insert these. If these vertex are not visited, we will insert these vertex in our queue. So these are the things. Remove 0 from queue and insert adjacent of 0 in queue if not visited. So there are two adjacent, 1 and 2, that are not visited till now, and mark 2 in visited. Okay. So we will mark that 1 is true and 2 is true, and 1 and 2 we will insert into the queue. So queue have a property first in first out. Okay. So those nodes are insert first, that will remove first. So here now one is inserted first, then 2 is inserted last. So we will next, in the next iteration, we will remove the vertex. So this one node will be removed, and so this is the next condition. Remove 1 from the queue and insert adjacent of 1 in queue if not visited. So those so that 3 and 4 are not visited in our adjacent nodes. So there are actually 3 adjacent here. So there is 0, 3 and 4, but 0 have already visited, so we are not looking that node. So 3 and 4 are not visited till now. So we will insert these 3 and 4 in our queue. 2 is already there in the previous iteration. 2 now 2 new nodes are added in the queue, 3 and 4, and we will mark that after. So next, after removing this one node from the queue, we will check that there are 2 adjacent nodes, those are not visited. We will mark that the visited. So now all the visited, all the nodes marked as true, visited. Now the next iteration, we will remove the next node from the queue. So now 2 node will be removed. Okay, but there is no adjacent node is available which are not visited. So there is no operation will be performed for them, because there is no node available which are not visited. So we will skip that part. Same things, we will remove the 3 from the queue, but still no adjacent node are available which are not visited. Same things, we will repeat this process for the 4. So we will remove this 4 from the queue and then check that is there any adjacent available, but no adjacent available. So same things we will repeat for this. Now our queue is empty. So this is representing that we have visited all the nodes in the graph. And in our visited list, if we check that, so all vertex marked as it 2. So this is the concept of BFS, and we can implement this concept using this program, which I taught in the lecture. So we are taking one queue here. Okay, and this is the BFS list algorithm. So here, this is the BFS algorithm using a adjacency list. We can perform in any using a adjacency matrix, as well as we can perform on the list. So here initially visited is empty. Initially we are assigning that all the visited node equal to false. So this is the table which we have already seen in the slides. So this is the visited dictionary. Initially all are false, and we are creating a queue using the upper class queue. Okay, this is empty initially. Now we will visited v equal to 2. So this v is we are taking from this function a list. So we are taking the information of the graph. So this a list is a representation of the graph, and v is the initial node. Okay, so where we will start from the we will start traversing. So we will assign this visited v equal to 2, and we will add this v into our queue. So this is the initial part where we are starting traversing from any particular node. After that, until queue is not empty, we will repeat this process. So we will remove one element from the queue every time. we will check that what are the adjacent nodes are available which are not visited. Okay, so we are checking here for k in a list. So what this value is representing, representing that what are the adjacent of this j node. Okay, j is the removed node from the queue, and we are checking that what are the adjacent nodes of this j, and after that we are checking the k is visited or not visited. If k is not visited, then we are marking that visited true, and we are adding this k into our queue. Okay, so we will repeat this process until our queue is not empty. So after completion of this process, we will return the visited list, so that visited dictionary, and then we will got this output. So now all nodes are visited. This true value is for every key is representing that every vertex is visited in the BFS form. Sorry, yes, Sandeep.
Yeah, so a small dot here in this part for k in a list j.
This one.
Yeah, sir. Yeah, sir.
Okay.
Here I'm not understanding that what is returning a list j here.
A list j. So a list j, actually a list is a representation of graph in the dictionary form. Okay. If you can see the so if we have already mentioned the adjacency list representation. Okay, I'm seeing you. Yeah. So undirected graph. This is there is one undirected graph here. Okay. And if we are representing this graph into our adjacency list form, so you can see that this is the form of adjacency list. Okay, so here 0 is a key. This is the vertex, and this 1 and 2 representing that there are two edges which are connected to 0. 0 to 1 and 0 to 2. Okay, if you see the graph, so there are two edges which are connected to 0, 1 to 0 and 2 to 0. So
0 to 1 and 0 to 2.
So in the undirected graph we can say anything. So 0 to 2 or we can say 2 to 0. Both are representing the same edge. Okay. So these information are representing the adjacent node. We can see. So all 2 and 1 are adjacent of this 0. Adjacent means directly connected by edge.
It means that a list j is returning those value.
Yeah, those actually a list are returning the nodes which are directly connected to that by any edge. Okay.
Yeah.
Yes. So here, so we will perform this operation completely until the queue become empty, and then we will get all the traversing information. So this these nodes are traversed according to the BFS concept, level by level. Okay, we can also perform BFS on adjacency matrix if we have a adjacency matrix representation for any graph. So we can also perform, but here the cost is high because finding the adjacent node takes order of n times. Here n is the number of vertex. Because if we are in the list, in the adjacency list form, we can directly check that how many adjacents are available. So if you see that, we can directly get this information. So which nodes are adjacent of the 0 in the list in the constant time. But in the adjacency matrix form, we have to check every column. For example, if we are checking that how many, so which nodes are adjacent of the node 1, so we will check all the columns value here. Okay, so how many vertex are, if 5 vertex are there, we have to check the 5 columns value. So we will check that so there is for one vertex there is one value that is representing one S, there is one value representing the second S, this one value is representing the third S. So there are 3 S, there are 3 adjacent vertex are available. So we have to visit all the columns value to check the adjacent nodes. So because of that, the complexity will be high compared to the using adjacency list.
List, yes.
Yeah. So here we are getting this information in constant time, but in the next using where is the algorithm? Yeah, adjacency matrix, we will get this information in order of n times. So because of that, the complexity is a little bit high. Yeah. So there is one function we are using here, the neighbors function. That function are for returning the adjacent nodes information. So you can see that we are using one loops for the columns of the matrix, and we are checking that if is the value of the I comma j is 1, that means that are the adjacent node. So we are appending the neighbors in the j. So after checking this information, we are returning this neighbor information into our BFS. Okay. So here this neighbor function we are using here. Same things, we are just getting this neighbor information using this separate function. Otherwise, all the concepts are same. Okay, so we are creating the visited dictionary, then we are creating a one empty queue, then we are adding a starting node in the queue, then we are removing one by one node, and then we are checking the adjacent node. If node are not visited, we are just mark them true and the adding into queue. Same concept, but the representation is different, and the information for the adjacent nodes we are taking the help of this neighbor function. So this is the BFS concept, and in BFS concept, using this BFS algorithm, we can get some extra information like this list of path from vertex v using BFS. So there is one application, you can see the application of the BFS. You can get the information, you can get the path from any particular node to any other nodes. Okay, so for getting this path information, we have to maintain one more dictionary here, that is called the parent dictionary. Okay, there is one dictionary we are taking, parent. This is initially empty. Initially we are assigning this parent information by -1 for each node, and so yeah, in this while in this while loop, so we are assigning a value here, parent of k equal to j. So this is the information where from we are coming on this k node. Okay, so here this j is representing the removed node from the queue, and this k is representing the adjacent of this j. Okay, so we are just storing this information where we are coming from actually. So k node we are reaching from j node. So we will mention that the parent of k is j, and we will using this parent information we can find out the path. So after storing all the parent information for every node vertex, we can find out the path. So for example, after performing this program, we are getting this parent information here. And how we can check the path? So we can check the path in the reverse order. So we just show you. So this is the output, and this is the parent information given by the out program. So parent of 0 is -1. This is representing the source. There is no parent for that. -1 value is representing that. This is the source node, and there is no parent of this node. After that, parent of 1 is 0, parent of 2 is 0, 3 is 1, and 4 is 1. For example, if we are finding out what is the path of 0 to 4, okay, 0 to 4, what is the path? So we will check that we will start from the destination node. We will check that what is the parent node of 4 in our dictionary. So we can find out the path using this. So what is the parent of 4 is 1. Okay, 1. So we can represent that 1. Okay, now we can check that what is the parent of 1 is. Now 1 is 0. Okay, so like 0, and there is no parent, that means this is the source. So this is the path from 0 to 4. Okay, so we can calculate the path in the reverse information. We will start from the destination and check the parent of every vertex until we reach the source node. So after adding this small information, parent information in our program, we can find out the path from the any source to destination. So this is one application. We can take the help of the BFS algorithm to finding the path. Next is find the label of vertex. So now we have already discussed how we can traverse the graph label wise. So we can manage this information, and we can also store this information, the label of each node. Okay, so what we are changing here in the same code. So this is also a similar code, just we are adding some extra information here also. So there is one label for each node we are taking. So this is also a dictionary. This parent is yeah, so this parent is included here, but that is the useful for finding the path, not the label. Okay, so we are taking just a label dictionary here, and initially all labels are -1, and same things we are performing the BFS algorithms. And so after yeah, so this is the source node. B is representing the source node. So we will first mention that this is the 0th label. So label of the source node is 0. We are assigning that. After that, here we are just removing the node from the queue, and we will assign the label of all adjacent node by using this equation. So because each k is the adjacent of j, so we will add the label value at the one value in the label of j to assigning the label of k. Okay, so if you mention that, if you see the previous diagram where I mentioned this information, so we are initializing this 0 label for this node. If we are finding that what are the adjacent node is 1 and 2. Okay, so this 1 2 we are coming from 0. So what is the label for the parent node is 0, label value is 0. So we will add the one value in this label, parent label value. 0 plus 1 is 1, and 0 plus 1 is 1. So next, this is the next label. Same things, and for the next label, so these 3 and 4 are the next label, and we are coming from this one node here. And what is the label value for this one node is 1. So we will add 1 into this value. So 1 plus 1 is 2, and 1 plus 1 is 2. So that means these 3 and 4 are at second two level. Okay, so we can find out the label information also using this BFS after some modification. So these are some information we can find out using this BFS algorithm, path and label. Now the next traversing algorithm is DFS, depth first search. Okay, so as per the name, depth first search, here we will traverse the depth first. Okay, until we can reach. So we are just taking the one new graph here. This graph is same. So 0, 1, 2, 3, 4. Okay, so this is the initial graph, and if we are starting from 0, so we can start from any node. Okay, this is the undirected graph, so we can traverse in any direction according to the edge, but in the directed graph, so for example, if this is a directed graph, so we can move it according to the direction only. Hello, for example, yeah, Vyas, yeah, sorry, what is the name? Saji.
Sorry, sir, I didn't hear. I was on.
Okay, okay, okay. Yeah. So if this is a directed graph, then we can move according to the direction only. So what are the edge? For example, if this is a directed graph, so we can say that the adjacent of 3 is 2, but we cannot say that the adjacent of 2 is 3. Okay, according to the direction. So this is the not a directed graph. So we can start from any vertex. Okay, so for example, if we are starting from the 0, here we will move depth first. Okay, so until we can reach from any vertex. So for example, if we are starting from 0, so we can move in any direction. So what is the direction to visit is 0 to 1 we can visit, 0 to 2 we can visit. Okay, so we can visit 0 to 1, also we can visit 2. So order of the DFS and order of the BFS can more than 1. There is no fixed order. You can see that there is a fixed answer. If we found the what is the BFS order is, what is the DFS order is. So more than one answer are possible in the order. Okay. So here we can start from 0 and we can move to the 1. Also we can move to the 2. Both are the adjacent of 0. Okay. So after visiting the first node, for example, if we have moved this one node, so we will check the next adjacent node. Okay, here we are traversing the depth first. So what is the depth? If we are starting from 0 to 1, then we will check the next depth of the 1. So we can move either in 4 and we can move either in 3. So here there are two possibilities. So if we are moving 0 to 1, so we can move 3 and we can move 4 also. Same for if we are 0 to moving 2, then we can traverse 3 and 4. So 3 and 4. Okay. So after reaching 3, so what are the next depth is 4. So this is the separate part we are talking about. 0, 1, we can move 0. Then next depth is, for example, 3. If next depth we are checking that we can move either 2 or either 4. So for example, if we are moving 2, then from 2 we can move also 4. So this is the one order we can traverse using DFS. Okay, so here there is no condition to traverse the all adjacent first. Here we will traverse the according to the depth. Okay, according to the adjacent depth wise. So we can start from 0 to 1, then 1 to 3, then 3 to 2, then 2 to 4. And we can also traverse 0 to 1, then 1 to 4, and then 4 to 3 and 3 to 2. Okay, also there are many possibilities are there. So 4 we can also traverse 2 and 3. Okay, so here we are traversing according to the depth. So there are many possible order to traverse the graph using the DFS algorithms. So if you see how we can implement this DFS algorithm, so we can take the help of stacks. This is the external thing. Otherwise, recursive approach is also use the stacks. So we can also perform this task using recursive algorithms. Okay, so both approach are here. So actually in the lectures are taught using the recursive solution, and here using stack solution code is also available. So you can perform in any way. So here we are starting from 0. We are just maintaining a one stack, same as the previous BFS algorithms, and there is one list visited. Here we are using the dictionary for that. So initially all are false, and stack. So there is this is initially this is empty, but if we are starting from 0, so we will push this 0 vertex into our stack. Okay, so you know the property of the stack. The property of a stack is last in, first out. Those nodes will edit the last, will remove the first. Okay, so we will repeat the process. So yeah, so there are two adjacent. We will check the adjacent and we will select any one of the adjacent every time. Okay, so there are two adjacent. 0 of the 0 node is 1 and 2. we will select either of any. So what are the adjacent of is yeah, pop 0. We will remove the pop. We will pop. Sorry, we will pop the 0 vertex from the stack and mark true if not visited, and push adjacent of 0 in stack if not visited. Okay, so there are two adjacent 1 and 2, and those are not visited. So we will push these adjacent these vertex in our stack. So we can push in any order. We can push in 2 first, then 1 last, and we can also repeat this order. So 1 first and then 2. So now that this variable top is representing that which vertex is the on the top last added. So here 1 is the last added vertex. So in the next iteration, what will be the popped element is 1. Those elements are at the top. So okay. So what is the next popped element is 1. So we will remove the 1 from the stack and mark 2 in our visited dictionary. If then check that the adjacent of the 1 is, if it is not visited, so 3 and 4 are adjacent which are not visited. Okay, we will add into the stack. Here we will remember one thing: if the any node is already in the stacks, still we will add again if that node are coming again. Okay, so here the adjacent of 1 is 0, 3 and 4, but 0 have visited, so we will not consider the visited node, and the unvisited node is 3 and 4, but both are not visited and also not are in the stacks. So we will push these node adjacent vertex into our stacks, and the next top is 3. So next iteration we will remove the top vertex, that is 3. Now 3. So here you can see that. So what are the adjacent nodes which are not visited here? So there are two adjacent nodes. There are 3 adjacent nodes of 3. So 2, 1 and 4, but 1 is visited, 2 and 4 are not visited, but 2 have already in our stack. Still we will add this. So 2 and 4 already have in already in our stacks. Still we will add these adjacent nodes again in our stacks. Okay, because here we are performing the traversing depth wise. Okay, so the order can be different. So now the 2 at the top. Okay, so next unvisited adjacent are, of the 3 is 2 and 4. So we will push these vertex into our stacks. Now 2 on the top. Now so we will once again in the next iteration we will remove the top element. So that is 2. So after removing these 2, now next unvisited vertex is 4. So we will push again here. Now this is a top. In the next iteration we will remove this 4 and mark visited is true. Now all vertex marked as true. Now the top node is 4, and there is no adjacent available for the 4 is to added in our stack. So in this iteration there is no operation will be performed. This is the skip part. So pop 4 from stack, but it is already visited, skip, and we will repeat that. Then now the next 4 is already visited. Now top is 2. If we will remove 2, it is already visited. Now stack become empty. So we can find out the traverse order using this DFS algorithm in using this stack data structure. So this is the approach we can perform. So this is the stack we are using externally, and this is the DFS list that are performing on the representation adjacency list, and this is the start node. Okay, same things, we are just maintaining the visited dictionary. Same thing, initially we are assigning all values say false. So there is one empty stack we are creating. Now we are post the first node where we are starting the traversing, and while the stack is not empty, we will repeat this process. So every time we will pop one element, check that if that is visited or not. So every time if we are pop any elements, we will check that node is visited or not. If node is not visited, then we will perform the next task. If already visited, we directly skip that part. Okay, so if J is not visited, then we will check the next thing. So we will mark that J is true, and then we will check the adjacent of the so we can remove this part. Actually, there's no meaning of this here. We can take in any order. So we will check the all adjacent of the J here. If the adjacent of the J is not visited, then we will push this value adjacent node is in our stack. Here we are marking visited equal to true in outside of this loop. We are marking the visited node when we are pop the element from the stacks. So we can find out the DFS order. You can traverse the vertex of the graph in the DFS order using this algorithm. So same thing, we can perform this DFS algorithm using a recursive approach. So see here the
ना तार नहीं चल ले जा खत्म हो गया ना तो दूसरा कोई तो कनेक्ट कर लेना खत्म हो गया.
So here DFS, so this is the initialization part. Okay, so initially all our parent information listed dictionary we are creating. Same things we can find out the path parent path information from this algorithm also. So visited of I equal to first, initially parent of I equal to -1, and then we will return this visited. So this is the initialization. This initialization we are using in our code. So DFS init list, where is this part? Okay, so actually we are using separately. So here we are initializing this part by calling this function, and we are performing this DFS list using this recursive approach. Okay, so every time we will check that what are the, we are just mentioning that so this is the starting node. Okay, and visited we are marking the true, and we are checking that what are the adjacent of the V is, and then if the adjacent node are not visited, then we will just inform, we are managing this information, what is the parent of the V is, what are the parent of K is equal to V, and then we are performing this operation on the child recursively. So same things, we are calling this DFS list algorithm on the child node. So this algorithm is also performing the traversing depth first search according to the depth first search concept. So this is the recursive approach. So this is the some different variant here. We are using the global variable visited and parent. We are assigning this global variable, then performing the same task. So there is nothing different in this program. The same things we can perform DFS on adjacency matrix. So we will use this neighbors function to find out the adjacent nodes, and all these things are similar. Same thing. So this is the some changing of the representation only. So these are two traversing algorithm, BFS and DFS. Now some application of BFS and DFS is find component using BFS. Okay, so what is the component is? So if you see the graph, how many components are there? So there are two components. Yeah. So there are two components. So component is, we say that those graph which are where the all nodes are connected. So if there is any path in between, so we can say that that part that is connected. Okay. So there is no edge between this 1, 0, 2 part of the graph to remaining of the vertex. So this is the separate component of the graph. So there are two components, two connected component. We can see that this is the separate connected component, and upper part is the separate connected. So how we can find the number of components in our graph? So we can this is the one application, find component using BFS. So after modification some information, after managing some extra information, we can find the number of components. So we will start. So if you see the algorithm, there is one queue. Okay, and this is the BFS algorithm. This is the same algorithm which we have already seen before, and this is the part where we are finding the number of components. Okay, so we will just check that if we are starting from any node, we will check that how many nodes we can reach from that source node. Okay, so initially, for example, if we are starting from this 3 nodes, okay, if we are starting from 3 nodes, we will apply the BFS algorithm, and after applying this BFS algorithm, we will check that how many nodes are visited. So if you will perform the BFS on this 3 node, so after performing the BFS algorithm, so this 3 will be visited, 2, 4 will be visited, 7 will be visited, 8, 9, and 5 and 6. These all become true, but the 1, 0, and 2 will remain the false. Okay, so we will apply this BFS algorithm on, for example, if we are starting from 0. So if we will first apply this BFS algorithm on 0, then check that how many nodes becomes true after applying this BFS on the 0 nodes. So after performing the BFS on 0, so this 0 will be true, 1 become true, and then 2 become true. Okay, but all the remaining will remain false. So after applying BFS on 0, we will check that all nodes are visited or not. If all nodes are not visited, then we will once again apply the BFS algorithm on any of the nodes which are not visited. Okay, so after applying the BFS on this 0 part, so there one component will be visited of the graph. Then we will apply the BFS algorithm on the second component. Those nodes are not visited. So we will apply the BFS algorithm on any node which are not visited. Then, for example, if we are applying the BFS on 3, so then 4, 7, 8, 5, 6, 8, 9 all nodes become true. So after that, we will check again if is there any nodes which are not visited, if the value of the visited is false or not. So after applying the BFS on the second component, so all become true. So we can say that there are 2 components. So first, when apply BFS on 0, so these 3 nodes are visited. Now the second time when we apply the BFS on any node of this second component, so all nodes are come true. So how many times we are applied the BFS algorithm, we can manage this information. We can store this information in any variable, and so we can return that the total number of components are 2. So same concept we are using here. So here we are actually there is one component dictionary. This is the initial empty, and for I in elasticity we are just assigning the all value -1. Component of I is -1, and there are 2 variable we are using, comp id and scene. These are initially 0. We are using these value to find out that how many nodes are visited or not. So while scene is less than max of a list keys. Okay, so here we are getting the total number of vertex. If the scene value is, so scene is containing the information how many nodes are visited and how many nodes are visited actually. Okay, so if this visited value is less than the total number of nodes, that means that some nodes are still remaining to visit it. Okay, so because of that, we are using this while loop. So we will update this scene when we will traverse any nodes for any component. So we will start. So this is the start V. So we will find out the minimum value of the vertex, any vertex. For example, we are starting from. So initially we have here how many nodes are 10. Okay, so 0 to 9. So we will check that what is the minimum vertex value in all these. So there is one 0 value. So we will just take the 0 value to traverse. So we will apply. So start, so that we will get the 0 value here, and then we will apply the BFS algorithm on this start. after performing this first VFS, we will get that the 3 node will be visited, 0, 1, and 2. So what will be the scene value is 3. So every time we are increasing the scene value. So this scene value is contain the information how many nodes are there visited. Okay. So after completing this one process, we will check once again. We will check that if scene is less than max, then we will repeat again. So here condition is given component of I is equal to -1. This information actually is representing that these nodes are not visited. Okay, so we are updating this component value here if node is visited. So those node value, those nodes component value is still -1. That means those nodes are not visited till now. So once again we will find the minimum vertex value from that part. So here the minimum vertex value is 3. Then we will take out this 3 from our set, and then we will apply once again BFS. Okay, so this
here.
Hmm?
Yes, me.
Yeah, Sandeep.
Here, while scene is less than or equal to, or only less than.
Scene is less than. Okay, so 9 scene is less than. Max is the value is 9. Actually, here we are returning the value of vertex. Okay, actually we are starting from 0. So 9 is the maximum value. Okay, so this will return the 9 value here, and here we are storing the how many number of node visited.
Yes, sir.
Okay, so if this value is become so this is 9. Okay, so this value is, for example, this become 8.
Yes, sir. Then it should be equal to also, no?
Okay. Scene is next. So for example, if there is one node separated, yeah, I think.
Yes, sir. Professor sir has also said that there should be less than or equal to.
Okay, I'll correct it. Yeah, this is some wrong. So for example, if there is one separated node, so that will not cover in that case. Okay, then we will add the equal sign here. Yeah. Okay, thanks for the pointing out. Okay, so this COMP ID, that is the that containing the main information, how many components are there. Okay, so for every part of this while loop, we are just adding one value in the previous value, 0, then 1, then 2. So that we will return in our answer. This is the component what we are returning here. Component I. Yeah, so component of I. Okay. So that is the same value component of it. So what is the component? Okay, so yeah. Actually, we are returning the complete dictionary. This is the information. So here we are getting the information for every node. So which node are coming from which component? Okay, so that means 0, 1, and 2. These are coming in 0 component. Okay, so we are just marking the component values from 0 to next value. Okay, so this 0 representing the first component, and this 1 representing the second component of the graph. So all the nodes 3, 4, 5, 6, 7, 8, 9 are coming into the second component. So these information we are getting. If we want to just total number of components, we can return directly the COMP ID value here. Return COMP ID. So we can find out the total number of component using this BFS algorithms. After that, there is one more concept. So discuss pre-post using DFS. That is also important numbering information using DFS, where we can find out the information of the cycles and other things. Okay, I'm just taking the slide of the lecture. The first. One second. application. Yes, slide is visible. Application of BFS DFS. Yeah. Okay. Yeah. So we can use this BFS DFS to find out the cycle of the graph. Before the cycle of the graph, we will just learn the pre-post counting numbering. So this is the connectivity. Where is that tree actually? Identify connected component. We already have connected component. Detecting cycle. Okay, so a cycle is a path, technically a walk that start and end at the same vertex. Okay, so if we find out if is there any cycle is available in the graph, so we can find out the cycle in using this BFS and DFS algorithm also. So detecting cycle is also possible. So here we are just considering the cycle. We are not considering that if, for example, for the undirected graph, so we are not just considering that 0 to 1 and 1 to 0 as a cycle. We are not repeating the edge in the cycle. Okay. So here 4, 8, 9, 4 is a cycle. So for example, 4, 8, 9, and 4. That color mark cycle is a cycle. So how we can detect this? So detecting cycle, yeah, so this is simple cycle we are finding out there. Only repeated vertex are start and end. Okay, cycle should not repeat edge. Cycle BFS tree. Okay, so here we are using the concept of tree, BFS tree and DFS tree. So we can represent the BFS tree. So this traversing, so we are just traversing the graph using BFS algorithm and DFS algorithm. So we can represent this traversing as a tree if we are starting from. Okay, so edge explored by BFS form a tree. So if we are so for I already create one diagram in the previous example. So if you have seen that, yeah, so that is the first. So here we are traversing. So for this graph, we have created this tree form. Okay, so first we are starting from the 0, then we are moving to 1, 0, then 1, then 2, then 3, then 4. So this form is we are called as a tree. Okay, so we can represent this traversing as a tree, and in the tree graph is cycle, so we can find out the cycle things. So what the edge represent the cycle in the tree is, so technically one tree per component. Okay, so if our graph contains more than one component, so for every component there is one new tree will be created for the BFS. Okay, so collection of trees called as a forest. So if there are 2 or 3 more than 2 tree is created by traversing of the graph, so that is called a forest. Please keep mic off. Okay. So BFS tree. So any non-tree edge create a cycle. So after creating a tree, after creating a traversing, and if we represent this traversing as a tree, so any remaining edge, which are not part a tree, that creates a cycle in the graph. So if we see the same example, so this is the tree representation, BFS tree representation. So this is 0 node, 1, 2, and 3, 4. So this is the BFS tree representation. So what edge we have covered in this? So we have covered this edge 0 to 1, and 0 to 2 we have covered, and 1 to 3. So 1 to 3 this edge is also covered, and 1 to 4. 1 to 4, yeah. So 1 to 4 is also covered. So other remaining edge which are not part of this tree, that create a cycle in our graph. Okay, so for example, if we see that 2 to 4, okay, so if we connect this 2 to 4, that create a cycle. Okay, So same things, if we just check 3 to 4, so 3 to 4 is also created cycle. So those edges are not part in the BFS tree that create cycles. So we can find out that so if graph have any cycle or not. So after creating this tree information, we can check that how many edges are remaining. If any edge are remaining, that means that edge are creating a cycle. So using BFS tree, we can get this information of the cycle. Same things, this DFS tree. We can also maintain a DFS tree using DFS algorithms, and we can also here we are just okay. We are including some information pre and post. So we are just assigning a number when we are entering any vertex and when we are releasing any vertex in traversing. So we are just assigning a number. We just call the pre and post. So here each vertex is assigned an entry number pre and exit number post. Okay. So if you can see that, so there are two components of this graph. Okay. So 1 second. So you can see that there are two components of this graph. First is this, second is this. So if we are starting from 0, so if we are applying the DFS algorithm from 0, so we will start from that 0, and when we are entering on any nodes, we will update the pre number, and then when we are releasing, when we are leaving any node, then we will update the post number. Okay, so these pre and post value will be help to find out the cycles. So we will see the later. First thing, how we can assigning this number on the graph. So you can see that so initially first we are starting from the 0 vertex. We will start this pre value as 0 on that node. Okay, so this is the similar to recursive call we will follow how we can just recursively call traverse in the DFS. So after traversing 0, we will check that what are the adjacent of 0 is 4 and 1, so we can traverse any one of them. So 0 to 1, for example, if we are traversing, so next entry node is 1. So we will update
which slide number are you studying?
8. This is the 7 out of 11.
It is visible only 6 for me, sir. Is it visible for all or only me?
Yeah, it is visible for me also. I mean, I'm seeing the 6th slide.
Yeah, sir. Only slide number 6 is visible for us.
1 second, I'm checking it. Slide number 6. B4. Where is the slide number? Every slide has same number. Okay, in upper side. So my current slides is not visible to you, where I'm marking something.
No, sir. Yeah, sir. It is not visible.
Okay, 1 second. Is it visible now?
No, sir. Still not.
Oops, yeah. Now
Now it is fine, sir. I can see the 7th slide.
okay. Okay, so I'm on that side. So we are just maintaining this pre and post number for every nodes, and we are just starting from the 0. So if we are starting from the 0, so when we are entering any vertex, we will just update the value of pre, and when we are leaving any vertex, so that is we will update the post value, exit number. Okay, so this is the separate thing. So here we are mentioning that, so we are starting from 0, so we just assign that pre is 0 for that 0 value. So in the next slides, you can see that we can traverse using DFS this tree, this graph. So we can traverse either 1 and we can traverse either 4. So if we are selecting to traverse like a 1, so we can move like this way using the DFS algorithm. So here we use the concept depth first. So if we are moving to 1, so we are entering to the 1, then we will update the pre value as 1. So this number we will increase every time. Okay, so we are getting the 0 value. If we are getting the 1 value, then we will add this. We will update this. Add 1 value in the previous either pre or post value. This is those value are the maximum. Okay, so if we are moving this 0 to 1, there is no node after that. Okay, so we will reverse back from the 1. That is the recursive call basically. So in the recursive call, if we are starting the DFS on 0, then we will again recursively call on the 1. So there is no node after that 1. Then we will return back to the previous node. At that time, we will update the post value for 1, because we are returning from that node. There is no node after that, and then we will never visit this node again. Okay, so we are just leaving this node, so we will update this post value. So what is the previous maximum value is 1, then we will update that post value for 1 is 2. Okay, so same things. Now the second path is from 0 to 4 side. Okay, so one path we have completely traversed, so there is no possibility to traverse other nodes after the 1. Then we will traverse the second path. So this is the 4. Okay, so now we are going to the 4, and we will update this pre value. Now 2 plus 1 is 3. Okay, now we can also traverse 4 to 8 or 4 to 9. So we can choose any one of them. So we are choosing the 8 value here. Okay, so we will just updating this pre value to 4, and then we can move 8 to 9. So next slide we can move. We are entering to the 9 node. So this is the pre value to 5. Same things. So there is no unvisited node after that. This 9. Okay, so we will start returning back from here. So we will update the post value. So this is the 6, and same things. We have reached the 8. So there is no new node to visited remaining. So we will just return back from here. So 8. So we will update the post value, that is 7, and then we will move to the 4 back. So there is no node are available to visit from 4 also. So we will return back. We will update the post value here 8, and then we will move to the starting node 0. So this is the 0 node. Now there is no path is remaining to visit from the 0. So we have completed this one traversing. So now we will update the post value for the 0. So this is the first first component is completed for the graph. So there are 3 components, you can see that. So there is one component, there is second component, there is third component. So total 3 tree will be created. Yeah. Okay, so second is this. Okay. So this is the 2 node. Okay, so the numbering we will remain the same from the last maximum value. So now this is the 10th listed number, pre number, and then we can move to the 3, 6, 7 in any direction. So we will just moving to the 3. So we will update the pre value 11, then 12 value for 7, Okay, so we are traversing using the DFS approach here. So same things, 6, this is the 13th, this is the 10th, 14th. Now I think all nodes are with 1, 2, 3, 4, 5, 6, 7, 8. So 1 is remaining. So after reaching 10, so we can move either 6. So 6 have already visited, so there is no node remaining to visit from 10. So we will return back from here. So at the time of returning, so we will update the post value. So now 14 to 15 is the post value, and then move to the 6. So there is no new node available from the 6. So we will update the post value here, 16. Now when we are returning back to the 7, so there is one remaining nodes are available, 7 to 11. Okay, so we will just move to the 11 node, and we will mark that the pre-value 17. Now no node is remaining from the 17, so we will update the post. So we will update all these value for all the nodes. 21. So this is the second component, and third is this is the last component, 5. This is the single, 22 and 23. So after creating these pre and post value for each node, we can get some information. So what are the information we can get? So there are some edge type here. So okay, so what is the node? Actually, we are just finding that what are the edge. But we are finding the detecting the cycles in the graph. So what are the edge contribute in the cycles? So there are 3 type of edge in this TFS tree, and the edge before non-pre-edge generate cycles. Yeah, so in the BFS tree, we can see that the non-pre-edge created cycle. Okay, so but in DFS tree, this is not a things. To compute pre and post pass counter via recursive DFS call. So one thing, this is the second part. Yeah, this is the. So there are 3 type of edge. We got this in the PFS tree. So this is a second different graph actually, and this is the tree with the information of pre and post value. So there are 3 type of edge we found in the graph. One is forward edge, second is back edge, third is cross edge. You can check these as by the color. So forward edge represent the tree edge as well as the edge from the last visited node to the next visited next visited node. Okay, so that direction is represent the forward edge. Back edge is represent to the latest visited node to the previous visited node. Okay, so that is called the back edge. So for you can see the red edge in the tree. So 5 to 10. So 10 have visited first, then 5 is visited. So there is one edge in the original graph. Okay, so we are seeing the original graph, the edge in the original graph. So there are the edge from the latest visited node to previous visited node. So that is called the back edge. And there is one cross edge also. So this is the cross edge, which are the different side of the tree. You can say that there is one edge from the left child to the right child. Okay, and this is also a this is the cross edge from the different childs. You can say that. So 3 to 6. So here this part is in the different side, and this complete part is in the different subtree, left subtree, or we can see the right subtree. These things. So there are edges which are connecting to the different subtree parts. So that is called the cross edge. So here only back edge create a cycle. Only back edge correspond to a cycle. So we can get this information. We can check that what are the back edge in our original graph. If is there any back edge in our original graph, so that means that create a cycle, and our graph contain a cycle. And this is the just representation of graph. We can see these things back edge, but we can also find out this back edge, forward edge, and cross edge using this pre and post value. Okay, so we have already counted assigning this sequence pre and post thing. We can find out this every type of edge using this pre and post value. So there are 3 edge. So first is pre edge and forward edge. Okay, So interval of, for example, if we are considering any edge u comma v, so we can find out that edge is forward edge, back edge, and cross edge. How we can find out this information is, so if you see any of the edge, for example, if you are seeing this 5 to 1 edge, okay, 5 to 1 edge, so here u is 5 and 1 is v. So you can find out that what type of this edge is. So here we will check that what is the pre value of u and what is the post value of u. So you can see the for u where what is the u is 5. So what is the pre value of u is 5 is 3. Okay, so you can see that 3 comma, what is the post value of is 6, and same we will check the for the v, pre and post. So what is the v value is 1, so 1 is this, so 1 is this, so 1 and 10. Okay, so we are getting this information, so we are identifying that what type of the edge is. So if the interval of pre and post of u, so what are the interval of 3 to 6, contain the interval of pre v and post v. So these 1 and 10 value are not coming in the range in between 3 to 6, that are the separate. Okay, that are the outside of, you can say that. Okay, interval of pre u, and so what are the interval of 3 to 6, but the value of the pre of v and post of v is 1 to 10. So these value are not coming in this range. Okay, that means this is not a forward edge. So what type of edge is, if you can see that back edge. Okay, so u and v, so here we are checking that pre v and post v contain the pre u and post u. So here we are just checking that, so what is the pre v and post v value is for that edge is 1 comma 10. Okay, and what are this information, this is for v and this is for u. So okay, so what is the value of 3 and 6? So you can see that the value of this 3 and 6, so pre v and post v, so this is the range from 1 to 10, contain the value of this 3 and 6. So these 3 and 6 are coming in this range in between. Okay, so if this condition is true, so that means for this as 5 to 1, this condition is true. So this condition is true, we can say that this is a back edge. And you can say that if the graph have any back edge, that means that graph contains the cycles. Okay, so we can find out these information, what type of edges using this. So there are 3 rules according to this pre and post value. So you can apply on these all these rules on any edge u comma v, and you can find out that what type of edge is. So if any edge is back edge, so you can tell that this is the back edge, and this is a part of any cycle of the graph, and graph contain the cycle. Okay, so we can get this information using this pre and post value in this DFS tree. Okay, so this is the help of this. Okay, got it. Any question in this topic?
Sir, cross edge, please once again.
Cross edge, so yes, you can see that, for example, actually we are looking this original graph. Okay, this is the graph. So if you remove the all colorful edge, so the original tree is actually 0 1 okay, so 1, then 4, then 5 and 6 black edge. We are just considering the black edge here, 2 and 3. So this is the original DFS tree. Okay, so 0 to 1, 0 to 2, and the all information, or for every all in pre and post information is given with the nodes. And after remaining nodes, so these are the nodes that we marked, that 0 to 1 we have marked 0 to 1. So this is a edge which is a part of the tree. 0 to 2, this is also a edge. 1 to 4, so this is also edge. And 2 to 3, so 2 to 3, this is also a part of the tree. 4 to 5, so 4 to 5, this is also 4 to 6, and 4 to 6. Oh no, 4 to no. What is this wrong? Oh yeah, 4 to 6 is also available. So this edge is also there. So 5 to 7, 5 to 7 is also this. So these all edge are part of the DFS tree, and the remaining edge we will check that what type of the edges. Actually, for detecting the cycle in the tree, we are just interested on the back edge, because this back edge is only the region for creating a cycle. Okay, so we will check all the remaining edges which are not the part of the DFS tree. So we will check this one.
In this tree, sir, 3 to 6 in the original graph, there is a edge.
Yeah, there is a edge, but this is not indicating that there is a cycle in the graph. But basically, we are defining the 3 different type of edge in the graph. So for detecting the cycles, only this back edge is important. Okay, so actually this 3 category we have divided, so tree edge and forward edge. So basically, if the edge are coming from that node which have already visited, so that is called the forward edge or tree edge. Okay, and back edge, if any edge are coming from the latest visited node to the previous visited node, that is called the back edge, and this edge is the region of the cycle. Okay, and cross edge is just coming from the another part. Okay, so cross edge means this part is visited separately, and this part is visited separately. Okay, there's no relation in between these two. So we are starting from 0. So first we completed this part, and then this part is separately visited. This is the second depth, we can say that. Okay, and is there any edge? Is there any edge from the for one separate path from to the another separate path called the cross edge? But that is not creating a cycle.
But I think, sir, here 6 and 7 is crosses, because of the pre and post value of 6 is 7, 8, and pre and post value of 7
yeah,
is
so
4, 5.
6 and 7 are crosses. It's already represented in the yellow color. You can see that.
Yeah, sir.
So this
That
is the
I'm like-
separate. This is the separate path from the 4, and this is the separate path from the 4, and there is one edge from these two separate traversing path. So because of that, we are calling this is a cross edge. But this is not creating any cycle.
Okay, sir.
Okay. So actually, we are just interested to find out this back edge using this pre and post thing, pre and post sequence numbers. So we can directly check this condition. If the pre of v and post of v contain the value of pre and u and post of u, if this condition is satisfied, that means that edge is back edge, and that is creating a cycle. Okay, so we can take the help of these pre and post numbers to find out the cycle in the graph, and others are some example which is not covered in this lecture and course. So just give some idea to how we can find out the strongly connected component using this pre and post information. Also, we can find out this what is this? So there are some also things. Yeah, identify the articulation point and bridge in the graph. So articulation point is what is the articulation point is if any graph. So for example, any graph So for example, if we have a graph 0, 1, 2, 3, 4, 5, 6. So what is articulation point is? Articulation point is any vertex. If we remove any vertex and the graph is divided into two separate components. If we are removed any vertex from our graph, and graph become in two parts, divided into two parts or two components. So for example, if we remove this one node from the graph, so our graph become as two separate components and divided into two separate components. So that node is called the articulation point. Okay, same things we can say that if we remove these two nodes, so after removing these two nodes, so there is one separate component. So our graph will divide into three components. That is also a articulation point. Okay, so and what is the bridge is, if we remove any edge from our graph and graph divided into two or more separate components, so that is called the bridge. So for example, if we remove this edge 1 to 2, this edge, if we remove this, then if our graph is divided into two or more separate components, then that is called the bridge edge. So we can also find this information using this pre and post numbering, but that is not the part of this course. So but you can remembering these things, what are the application, where we can use this pre and post in the DFS tree. And see the pre and post things. After that, yeah, DAG. So next topic is the DAG. So directed acyclic graph. So what is the directed acyclic graph? Is a directed graph with no directed cycle. Yeah. So there is one important condition is, so the no cycle should be there in the graph. That is, it consists of a vertex and edge with each edge directed from one vertex to another, such that following those directions will never form a closed loop. This is the condition of the DAG. First condition is that the cycle should not be present in the graph, in the directed graph, and also one or more than one vertex should contain the in degree 0. Okay, so these are two conditions for the DAG. So we can, if the graph contains these two properties, we can perform this topological sort and others algorithms also. So you can see that this is a graph. So you can see that this is a graph, and there is no cycle in this graph. If you see the direction by cycle, there is no cycle in this graph, and there are some nodes available which contains the in degree 0. What is the in degree and out degree is? So in degree is how many edges are coming any particular vertex, that is called the in degree, and out degree is how many edges are going outside to from that vertex, that is called the out degree. Okay, so what is the in degree of 1 is 0, and what is the out degree of 1 is 2, because two edges are going from the vertex 1, but there is no edge coming on that node. So because of that, in degree is 0. So this DAG should contain any one or more than one vertex which contains the in degree 0 also. So if the graph contains this to satisfy these two conditions, we can perform the topological sort. So topological sort is we will start from the node which contains the in degree 0. We can, if more than one vertex are available with in degree 0, we can start from any node. Okay, So if you see this graph, so initialization, so this is the algorithm. Basically, we will use the in degree list that contains the in degree information of each vertex initially, and we will just also maintaining a dictionary topo sort. Okay, so for every vertex that is already visited or not. So initially all value are empty. Okay, so just wait here. So initially 0 and 1 vertex have in degree 0. Okay, so if you see the 0 and 1 vertex, so there is no incoming edge on that node. So that is the in degree 0, and other nodes have some in degree. Okay, so we will start from either 0 and 1. So in the next slide, if you see, so for example, if we are starting from the 0, then we will remove this vertex, and we will also remove the edge which are going to this from this vertex. Okay, so now 0 have visited, so we mark that, and 0 is visited, and after removing all outgoing edge from the 0, so in degree will be updated for each node, not each node. Those edge, so edge which are connected previously from that node which we have removed, so we will update the in degree of adjacent node of that node. So after removing this 0 node, we will update the in degree of so what are the connected node was that 2, 4, and 3. So there are 3 edges outgoing from 0. So 2, 4, 3. So we will update after removing this 0. We will update the in degree of 2, 3, and 4 in our in degree information. Okay, and after removing the vertex, we will mention that the -1 degree for that node. Okay, so after updating the in degree of all connected vertex, so we have 3 vertex which have in degree 0. So we can select any one of them, and then we can remove that. So for example, if we select the 1, then we will remove all the edges from that node and update the in degree of all the adjacent node. So after removing the 1, we will update the in degree. Now we have once again we have 3 vertex which have in degree 0. We can select any of them. So same things we will repeat it until all the nodes will be removed from the vertex, from the graph. Same things we will repeat again and again. So now after 4 is in degree 0 and 5 is in degree 0, so we will select the 4. So after removing 4, then 5 have in degree 0, then we will remove the 5, then 6, and then 7. So this is the topological order. We are performing this topological sorting algorithm. How we can perform this sort of topological ordering on the DAG graph. So this is the concept of topological sorting. So basically this topological sorting used to perform many to solve many problems. So there are some examples to, so for example, if you are planning to doing any course and there are some prerequisite for to enter any course, so how you can complete your all the courses in the minimum number of semesters. So many type of problems can be solved using this topological ordering concept. So there is one more algorithm is also related to this topological sort. So longest path in DAG. Okay, so same things we will perform this topological sorting. The same concept we will perform, and at the time of we will contain the information of this longest path. So if you see that same things we will repeat, but here we are also just maintaining the information of this longest path. So initially, okay, I'm just opening this lecture slide where this information is mentioned clearly. Yeah. So directed assignment graph, longest path. Okay. So this is the graph, which initial graph. So we will assign the in degree of each, not the each. So there are some nodes which contain the in degree 0, and we will assign the longest path to I equal to 0. So if you see that, this is the graph. Yeah, this is one. So for longest path computation, you can see that initially, so this is value 0. This blue color is representing to the longest path value, and this 0 is representing to the in degree value. So there are two vertex are available with in degree 0. We can start any from any one of them. So if, for example, if we are starting from 1, so the longest path is here now 0. After removing this one node, so those nodes are adjacent of this 1. So we will adding one value in the longest path value of this one node to finding out the next longest path for 2 and 7. So after removing this, you can see that yeah, so these values are updated 1. So after removing 1, this longest path value, that means we can reach 1 to 2. So that representing the one edge. So here path, we are mentioning that how many number of edge we are covering from when we are coming to 2. Okay, so 1 to 2 when we are coming, so there are one edge we are covering. So this value is updated. So the longest path value for 1 was 0. We are adding the one value into that 0 value. So 0 plus 1 is 1 for 2 and 7. So two value are updated after removing one node. Okay, so same things we will once again remove the second vertex which contains the in degree 0, and every time we will also update the in degree which are affected after removing. Okay, so now this second 0 vertex contains the in degree 0. When we are removing this, so what are the longest path value of this 0 is 0. So same things. So we will add the one value in this 0 value to the adjacent longest path value. So initially, so this is the 1, this is the 0, and this is 0. And what are the initial source longest path value is 0. So we will add 0 plus 1 and update the longest path value for all these 2, 3, and 4 after removing this. So you can see that 0 plus 1 is 1 here, and in the next slide, 0 plus 1 is 1 here. So 0 plus 1 is 1, 0 plus 1 is 1. So all longest path value, that means we can come at this 2 vertex, 3 vertex, and 4 vertex in the one edge visited from the 0 or either 1. Okay, so same things we will perform the next. So for example, if we are removing this 3, so what is the longest path value? Is 1. So we will add the we will update the longest path value of 5 and 7 by adding one value into this one. So 1 and 1, 2. We will update this 2 value for 5 and 7 in the next part. You can see the 5 and 7. We will update this 2. Same things we can remove 2 or 4, any one of them. So if we are removing this 2, so what is the longest path value was is 1. So after removing this, 1 plus 1 is 2. So that it will still remain 2. Okay, same thing when we remove this 4 is, so 1 plus 1 is 2. Let's see what we are removing. Yeah, we are removing this here 5 is, so 2 plus 1 is 3. Now it becomes 3 here. This is 3. And if we are removing 6, then 3 plus 3 plus 2, 3 plus 1 is 4. So it becomes a 4 here. Okay, so after removing this 1, so we will select the maximum value which we have previously defined by removing the previous node. So that will remain the 4. So this is representing that this is the first node. This is the initial node. This is also initial node. For vertex 3, we can visit vertex 3 after visiting one edge, and we can visit vertex 2 after visiting one edge. So we can visit vertex 5 after visiting 2 edge. That contains this information. Oh, okay. So 4 is updated by this 1 plus 2. 6 plus 7. Oh, 7 is here. 7 is yeah, 7 is given here. Yeah, 7 is 4. So we can find out the longest path. So how many as we can traverse to reaching from any initial node to any other node. So this algorithm we can use. So this is also a yeah. So this is the last topic of that this week. So these are the code related to the same concept we are using. We are just maintaining this in degree, 0 degree, and L path, and we are just updating every time this information in this code. So this was the last topic. If you have any query, then you can ask. So any query, any in this week 4 and week 3, if you have any question, you can ask now.
Sir, in this course PDSA, when mock will be a start for quiz 1?
Yeah, so we will release one mock before the quiz 1, and this is the only one mock we will provide for the quiz before the quiz 1.
When it will be, sir?
Yeah, we will release in the next week.
Okay, sir. After this month.
Not this. So what is the date? 25. No? So yeah, we will release first Monday or Tuesday the next week.
Okay, sir.
So when for the proctored exam, when mock for that will be released?
Yeah, so there is one quiz exam now on 5th June.
Yeah.
So we will release the mock quiz before that, before 4 or 5 days before that.
Okay. And this proctored exam will be happening on the same day on 5th, during 5th and 6th, or it will happen after that?
No, what is the proctored exam? So
Programming.
for PDS there is no proctored exam or in this month.
Sir, the proctored exam is on July.
Yes, it is.
So there is
proctored
only
exam.
one. Yeah, there is only one proctored programming exam that will be happening after completing this all 11th, 12th weeks. That is in the July. Before your term exam. So before, I think so 10 or 12 days before the term exam. So only one proctored programming exam.
Okay.
So are you so how many are there? So 13 is there only. So are you participating in the CodeSafe competition or not?
Yes, I have some problem. So when I am logging, then it is saying that it is a state.
So
This
have you
type of
filled the Google Forms which Omkar?
Yes, I have filled, but by mistake I have filled my username wrong.
So just post on this thread if you see in the discourse thread which Omkar is handling. So
yes, I have posted on Discourse, but not still any response.
okay. So what is the name of
Username I can chat. May I chat, sir?
So you can just repost again, okay, on the same thread. Then I'll ask.
Sorry, sir. Sorry, sir.
You can repost your thread in the same thread. Then I'll ask to Omkar if he can help.
Okay.
Okay.
Yes.
Okay. Hello. Yeah, any other query?
Sir, as the weeks go by, we getting towards screen object.
No, you are not audible properly. So can you repeat?
Sir, as we spoke, we will get more codings and object-oriented programming.
No, so object-oriented programming, we are just using the class concept. So you have already started this class concept in the code, I think. So for the graph, you have already. So there are some codes which we are using create a stack and queue, and you have already learned the how we can create a linked list using the class methods. So after that, we are not using any inheritance or overloading, overriding this type of concept in this course. We will learn. We will simply learn the algorithms. Oops
Sir,
concept. So this is not a oops related course actually.
Sir, in quiz one, what should be prepare for quiz one?
Quiz one, no? So the syllabus for the quiz one is till week 4. So main focus will be on the week 2, 3, and 4, because the week 1 is just revising of the Python concept. Okay, so just revise all the concept. So focus only on the concept. Okay, more on the concept. So for example, if we are asking the BFS and the DFS, we are learning this. So don't need to learn the implementation, just learn the concept, how we are solving these problems. What are the concept you have?
But the implementation is necessary for
solving the
programming.
Programming assignments. These are the necessary, but for the quiz, the main focus will be on the conceptual person. So like your graded assignments, a graded theory assignment, practice theory assignments, the person will be based on the similar types of some. So maybe 2 or 3% maybe depends on this programming part. So there is program is given, and we can ask some information from that. So otherwise, most person will be on the concept basis. Okay, and you can also take the help of the previous term papers, which are also available. I think some sites is created by the previous term student. You can also see the previous.
Where it is available, sir?
Yeah, I also not have the link of that site, but if you visit the discourse thread, previous threads, so you can easily find out it. Okay, just visit the discourse of the threads of the PDS. So you can easily find out the previous paper. Okay, and otherwise we will also release the mock, so you can also get the idea of questions. Okay. Any other question? Okay, so there is no question, so shall we close?
Yes, sir. Sir, I have one personal doubt.
Yes,
not personal, sir. So, what all can I do after pursuing this degree? Yes, sir, in which field I can go, and what innovative I can do?
So currently you are in diploma, no?
Yes, sir. I'm diploma.
So what's your interest actually? Are you going in the data science line or just application development line?
Sorry, sir.
So what is your interest actually? Are you interested in the application development or in the data science domain?
Application development, sir.
Application development, no? So this is your interest, so you can move to the any software development company. You can prepare well in the programming part and just application development part. Focus on that part, then you can move any application development company, software development company. So this is your interest. This is totally depend on your interest, but focus more on the programming part. Okay, so sometimes programming question are we got the frustrated, and we are not we are trying, but problem is not solving. But that is a part of the learning. So just create your interest in the programming and learn, and just apply this programming part to develop some application, small application that uh, you, you can create your interest more in this field.
Okay, sir.
Okay, so what subject you have taken in this time?
Yes, PDSA, DVMS, and BDM, sir.
DDM. Okay, so currently you are not taking AppDev subject, no?
No, sir, until now.
Okay, okay.
After
So
this time, I will try.
okay, fine. Yeah, so the DVMS and Python you have completed in the foundation level. Then PDSA you will complete in this term. So yeah, so you can join the in the next term AppDev one, and also Java is also a concept for understanding the object-oriented concept. You should join the Java subject. Then you can
Yes, sir.
move to the application development. So we are using the Flask platform to develop the application. So create create your interest in this field and just learn all these things.
Okay, sir. Thank you, sir. Yes.
Okay. Okay.
Bye, sir. Good night, sir.
Okay. Bye everyone. Good night.